So, very good morning to all of you. And today's target is basically the properties of Pauli's spin matrices. If you rightly remember, yesterday we solved a problem based on Pauli's matrices, and we tried to calculate the probabilities. We tried to calculate the probability of having spin in either of the directions. Okay, probability of having spin along positive of x, along negative of x. Now today's target is basically, again, I would like to go with the properties of these Pauli's spin matrices, because these matrices are acting as operators. What you have in classical mechanics, you have observables. Okay, corresponding to those observables, you have operators in quantum mechanics, right? So let's try to have a conceptual overview of these Pauli's spin matrices. So they are basically very fundamental tools. Okay, they are very fundamental tools in quantum mechanics, and they are used to describe the spin of the quantum mechanical particles. Now, you have atoms as quantum mechanical particles, electrons as quantum mechanical particles, and protons as quantum mechanical particles. So these spin, these matrices are very fundamental tools that can be utilized to understand the systems that belong to these quantum particles. Yes. Okay. So they will be acting as a kind of machines. Okay. These operators are acting as machines. They work on your systems and they'll give you the probabilistic results, the results that you are interested in. Right? Okay. Can I move on? Okay. Now, what are these Pauli's matrices? They are basically a set of three matrices: sigma x, sigma y, sigma z, as we talked about. Okay, and what they do is they represent the spin operators for the particles whose spin is plus half and minus half. And they do have these corresponding directions: x, y, and z. Sigma x, sigma y, and sigma z. Now, talking about the core properties of these matrices. Now, each matrix corresponds to a direction in space. So you have a matrix that will represent the direction in the space, right? That's the first point. Now, what they help describe how quantum spin behaves under various conditions. Okay. What are these various conditions? You have spin, okay? It is an intrinsic property, and you try to interact with the spin. Say, for example, you use external magnetic field, okay? So these operators lead us to understand the interaction of the disturbances. I may call it a disturbance for the time being. The disturbances that leads us to understand these spins. Okay, they are essential in quantum computing. I talked about it when I introduced you with the subject. I believe that the basis of the modern quantum computers is the spin kind of thing, and certainly we work with these spins at very low temperatures when we talk about IBM, a quantum computer that's being designed in IBM. So these Pauli's spin matrices, they play a very important role in designing the gates. We have quantum gates. In classical world, we have the classical gates. You remember those gates? AND gate, OR gate. But these are classical gates. But when you have to design something based on the laws of quantum mechanics, you have the gates, and Pauli's spin matrices are very fundamental operators to design those gates. So certainly they have implications in quantum computing and they have implications in quantum information.
सर मेरा एक सवाल है।
Yes, yes.
सर अभी आपने बोला जो ये पॉली मैट्रिसेस होता है तो इसमें मेनली हम लेते हैं 1/2 और -1/2 ऑपरेटर्स हम लेते हैं।
Not operators.
मतलब कि ये हम लेते हैं इसलिए हम ले रहे हैं।
We know that we don't take them as 1/2 is basically no, you are asking.
सवाल
Yeah.
अब सवाल मेरा यही है कि आपने बोला ना अभी कि क्वांटम कंप्यूटिंग के लिए हम ये यूज करें मतलब और गेट के लिए या एंड वगैरह के लिए।
Yeah.
और के लिए हमें पता है कि
No, don't say or. We have different gates here.
और
Okay.
गेट के लिए मतलब कंडीशन है कि एक होना चाहिए ट्रू तो सारे ट्रू है लेकिन उसके लिए कैसे मतलब कि 1/2 क्या इसमें प्ले करेगा या 1/2
Okay, it's a very beautiful question basically. See, when you talk about the classical computing, you have only two possibilities, 1 and 0. Okay, 1 and 0. We call them bits. But when we talk about quantum computing, when we talk about a quantum operation, say for example, spin. Now, what she says is that we have spin plus half and minus half. But we don't have only these two states. The spin of the particle can be in a superposition. So you can have both the possibilities for the spin of this particle. Your particle will have both realities with it. It will have a spin of plus half and it will have a spin of minus half in its superposition state. Now this seems too little. But when we talk about the superposition, if we think about this particle having spin up and spin down, there are infinite possibilities between plus 1/2 to minus 1/2. So your system is in quantum mechanical superposition and you have to exploit that superposition. And when you exploit that superposition, I think you should watch my video on quantum computer. I have delivered that lecture in Women's College on quantum computer. You can watch that video and you will understand. You will notice there I have talked in very simple words that how does a quantum computer work. So here we have a range of possibilities. Your machine can do many actions at one time. So why you are talking about OR gate?
मेरा एक क्वेश्चन है ना
Yes.
अब देखिए +1/2 हम फिर ले रहे हैं और ट्रू के लिए OR गेट मैंने एग्जांपल दिया आपने लिखा ना क्वांटम कंप्यूटिंग के लिए मैं OR गेट का बोल रही हूँ उसमें होना चाहिए कि एक कंडीशन ट्रू तो सारे ट्रू है।
So these are two different frameworks.
तो मैं यही बोल रही हूँ कि जो +1/2 है जब हमें +1/2 होगा तब हम उसको माना है ट्रू और -1/2 के लिए OR मतलब false।
Yeah. But that's your classical intuition, okay? That the thing that you are talking about is classical thing. What we are talking about here is you have a machine that's working on the principles of quantum mechanics. Okay? Your gates, the gates that you have learned in electronics, they are working on classical laws of physics. They are not working on quantum laws of physics. So why they are important? As I was telling you, the answer to your question was in this slide. So Pauli's matrices, what they do, they capture the essence of quantum behavior, okay, such as superposition. This is the main tool of quantum computing and measurements in a compact and powerful form. Now see, this is very powerful. Let me tell you frankly, if you can have a quantum computer of 100 qubits, it will perform its operations which will be many fold faster than that of a supercomputer that you have. Okay, so here things work very fast. So that's a different course of subject. I would not like to go into the details of that. Okay, so they do have applications. What we do is we describe the quantum spin using these Pauli Spin matrices. We can talk about the magnetic resonance, as I talked about that in the previous lecture. quantum computing, gates like X gate, Y gate, and Z gate. So here we don't have OR and kind of gates. We have gate like X, Y, and Z, and these basic gates can be built using Pauli spin matrices.
Magnetic resonance.
Yeah. Magnetic resonance, I told you. Yeah, come on, what is magnetic resonance? I'll give you an example of that as well. Come on. Even though I talked about that medical equipment that we have, what's that called? MRI, magnetic resonance imaging. So you can have an interaction between external magnetic field. What is MRI? You have very, very strong magnets, and these strong magnets are built in using superconductors. These are called superconducting magnets. Okay, so what they do is they interact this magnetic field with the spin of the particles that a person is made of. So this interaction leads to the resonance, okay? And this resonance can be mapped in the form of an image. So you can see actually what's going on in your body, right? So that's what magnetic resonance is. Is this clear?
And the fourth one.
So this is a different state of topic. Okay, we will not go into the details of quantum entanglement. You can check it out on other videos if you are interested. Come on, this is the end of it. Okay. So now let's go with what's our target today is to learn some of the important properties of these Pauli matrices. And I have some target in my mind, and I want to reach out to that target. So let's exit from here. Come on. Okay, so what we'll be discussing here is the properties.
So we matrix बनाना है ना पहले. वो कैसे होता है dividers?
All right, fine. So yeah, what else?
मैट्रिक्स बनाना है ना कैसे होता है वो? क्योंकि आपने बोला ना वो 3 मैट्रिसेस होते हैं.
Yes.
बोला ना कि वो 3 मैट्रिसेस होते हैं. वही कैसे?
Yes, we have built with them yesterday. Okay. No, you just check out what I'm showing you. Okay. So what we have is we're going to talk about the properties of these matrices. So what we have, let me write down. We have to write down Pauli matrices. So what are they? Number one is sigma x, right? Number two is sigma y, and number three is sigma z. Now sigma x is what? This is 0, 0, 1, 1. This is 0, 0, minus I and I. And sigma z is 1, minus 1, 0, 0. Right? These are our Pauli spin matrices. Okay, we have sigma x on x, then we have sigma y, and then we have sigma z. Now the very first property of Pauli spin matrices is that these operators are Hermitian operators. Okay, so if they are Hermitian operators, then they must be equal to their own adjoints. So if you take the adjoint of the Pauli spin matrices, you should come up back to the original matrix. So let's verify this fact that these operators are Hermitian operators. Come on. So what we have for that, sigma x must be equal to sigma x adjoint. Now what is sigma x? Come on. Sigma x is 0, 1, 1 and 0. Okay, you take its transpose, that will be the same thing, 0, 1 and 1, 0. And take its complex conjugate and we'll get the same thing, that is 0, 1 and 1, 0. Right? So what you have done, you have checked that the adjoint of the spin matrix, Pauli spin matrix sigma x is equal to the same matrix. And we can test this thing for sigma y, and we can test the same thing for sigma z. So for sigma y, come on, what's sigma y? Sigma y is, it is 0, 0, minus I and I. Come on, take its transpose, that will be 0, I, minus I and 0. Getting my point? Okay, you have taken its transpose, and now you will take its complex conjugate. So if you take its complex conjugate, yes? No, I have taken the transpose of this. When you take the transpose of a matrix, you convert your columns into the rows, okay? So that's why you have plus I here, okay? Now I'll take its complex conjugate. So what will happen? You will have 0 minus I, then you will have I, and again you will have 0. So what does that mean? That means sigma y is equal to the adjoint of sigma y. Confirm? Okay. Now the third part is the same thing. That's clear. That's clear. Come on. Maybe I'm going fast. You copy it. Come on. Come on. Okay. So what do you get from here? You get sigma x is equal to sigma x adjoint. Sigma y is equal to sigma y adjoint, and sigma z is equal to sigma z adjoint. So this thing verifies the fact that these operators, these Pauli spin operators, are Hermitian operators. Clear? Okay. So the property number 1 is gone. Now the next important property is inverse. You may also call it as involuntary property. Now what is it? It is something, if you have some operator say x, this x must be equal to its inverse. So how can I test it? How can I test an operator has a corresponding inverse existing in it? Come on, how can I test it? Very good. So I will multiply the two, and if I get an identity, that will confirm that there exists the property of involuntary. So let's take our sigma x. What's that? That is 0, 0, 1, 1. Right? Okay? And let me take sigma x square simply. So what will be that? Times 0, 1, 1, 0. Am I right? I have taken square of sigma x. So what you will get here, come on, multiply this. Come on, this will give me 0, then plus 1, and this will give me 0, then plus 0. Okay, this will give me 0, and this will give me 0, and this will give me 1 plus 0. 1 plus 0. So what you will get? You will get 1, 0, 0, 1. And what is it? It's an identity matrix, right? So if sigma x square is an identity matrix, that means, what does that mean? Come on. That means sigma x is equal to the inverse of sigma x. Is this clear? Yeah? Can I move on? Okay. So in this case, what you will have is, so you have proved that sigma x is equal to sigma x inverse. You can check the same thing for sigma y. Now what is sigma y squared? What is sigma y squared? Come on. That is 0, 0, minus I and I. Multiply it with the same matrix. 0, minus I, and 0. Is this clear? Is this clear? Okay, fine. So let's multiply the two matrices. Okay, what you will get? Here you will have 0, and Iota will give what? Iota square. Iota square is minus 1. Minus 1. Minus will give us plus 1. So this I'll get 1 here. Okay, this is 0 plus 1. Is this clear? Okay, this is the first term. What about the second term? This will give me 0 and this will give me 0. The third term, come on, this will give me 0, am I right? Plus, and this will give me 0. And the last, iota square again. That's minus 1, minus will become plus. So here you'll have 1 plus 0. So what you are getting? You are getting 1, 0, 0 and 1. What is it? It's an identity matrix, right? So if it is an identity matrix, you can simply say that sigma y is equal to sigma y inverse. Fine? So I think you can obtain the same thing for sigma z. So what we have obtained two conditions, right? What was the first condition? The first condition was sigma I equals, sigma I adjoint, right? This is what we have proved. What was the next thing? The next thing was sigma I equals to sigma I inverse. Am I right? Right? Fine. So you can see there are two equations. The left hand sides of these two equations are same. So you can obtain another important property. Here you can go for I as x, y, and z. Right? Because I can run from 1 to 3. Okay, you have three coordinates of your Pauli Spin matrices. So on comparing these two, what you are obtaining? You are obtaining sigma 2 inverse is equal to, this is I, okay? Sigma I inverse is equal to sigma I adjoint. Is this clear? Come on. Okay. So, gone with it. The next important thing is, well, let's try to obtain the determinant of these Pauli spin matrices. Okay. So now let's try to see the determinant. Determinant of Pauli spin matrices. Come on. Sigma x, what is sigma x? Sigma x is, it is 0, 0, 1, 1. This is sigma x, right? I want to calculate its determinant. So if I have to calculate its determinant, that will be sigma x. So you know how to calculate. You have the cofactors to multiply them. So 0 zeros will give us 0, minus 1 will give us 1, so it's minus 1. Is it fine? Now looking for sigma y. Come on. What is sigma y? It is 0, 0, minus I and plus I. Okay? So take its determinant, that's sigma y, the determinant of sigma y. What will be that? That is 0 minus iota square. Minus iota, so see here we have original minus. Okay? Original minus and the minus that you will have here, that will make plus. And finally you will be left with iota square, and that will give us minus 1. So I will write here minus 1. Am I right? Okay? The last thing is what? The last thing is sigma z. And what is that? Go on. That is 1 minus 1, 0 and 0. And its determinant. The determinant of sigma z.
Plus 1 बनेगा ना?
Yes?
आप ये फिर से लीजिए।
Yeah.
क्योंकि वहाँ पर है ना, वहाँ पर iota square होता है minus 1 के बराबर।
Come on, look at me. Come on. See.
फिर iota square होता है minus 1 के बराबर और अब
Yes.
minus से वहाँ पर minus minus।
But there is another minus of solving. Okay? There is another minus that you use to solve the problem. So now the determinant of this is what? It is again minus 1. So what do you observe? You observe that determinant of sigma I is equal to minus 1 and your I is running from X, Y, and Z. So this is another important property of Pauli's spin matrices, right? Okay, now the trace of these matrices. Now what is the trace? Trace is simply the sum of the diagonal elements that are present in a matrix, right? So the trace of sigma x, come on, you tell me now directly what's that? It is 0. Come on, calculate it, right? So trace of sigma x is 0. Now the trace of sigma y is 0. The trace of sigma z is 0. Clear? Okay. Fine? Everything fine till now? Any queries? Okay? Okay, okay. This is going on. This is how we are going on. Now, we have Pauli's spin matrices, right? And we define them as sigma x, sigma y, and sigma z. And we have to operate our operators on an eigenstate. And when I will operate my operator on an eigenstate, what will I obtain? I will obtain the eigenvalues. Why I will obtain the eigenvalues? Come on. Why I will obtain the eigenvalues? Because these matrices are Hermitian operators. They are Hermitian operators. If you go back to the problem of hydrogen atom, okay, you have Hamiltonian there, Hamiltonian operator. And what you get, you obtain energy eigenvalues. Why you obtain energy eigenvalues? You obtain them because the Hamiltonian that you have there is a Hermitian operator, right? So what am I saying here is that these Pauli's spin matrices are Hermitian operators. Now if they are Hermitian operators, and I will define, say for example, I will take a state, let me choose a state zeta, the ket of zeta, okay? I chose a state, ket of zeta. And I have sigma. I have, what is sigma? It's a Pauli matrix, okay? This sigma will act on this zeta, right? It will act on this zeta, it will act on this state vector, it will act on this eigenfact function, right? What you will obtain? You will obtain eigenvalue, lambda, and you will come back with zeta. So this is my energy eigenvalue equation. And from this equation, what can I calculate? I can calculate the eigenvalues. And I can calculate, and at the same time, I can calculate the eigenvectors. Because we are living in the domain of quantum mechanics. And when we are living in the domain of quantum mechanics, you are living in the domain of superposition principle. Right? Right? How we calculate the eigenvalues? How we calculate? Now let me choose this as sigma x. Okay? How we do that? Yeah? We say that the determinant of sigma x minus lambda I is equal to 0. Right? This is the equation that we use. Okay? Now let's solve this equation. I know what is sigma x. I have to calculate the lambda. I want the eigenvalues for my problem. Right? So let's proceed. So what I'll have, I will have sigma x. What is sigma x? It is 0, 0, 1, and 1. Then minus lambda times the identity matrix. What's that? 1, 1, 0, 0 is equal to what? It's equal to 0. Am I right? Okay, you can take this lambda inside. This is 0, 1. This is 1, 0. So this is minus. So this will be lambda 0. 0 lambda is equal to 0. Fine? Okay, now I have to subtract the two matrices. Their order is same, so I can subtract them. The two will lead us 0 minus lambda is what? It's minus lambda. 1 minus 0.
So how would you determine?
Yeah. Come on. I have done
How would
something
you
wrong.
determine it?
Yeah.
So तो पहले solve होता है.
Yeah. Wait. Okay. So I will subtract these two first. What am I getting here? I am getting 0 minus lambda. This will give me minus lambda. Then you'll have 1 minus 0. That will give me 1. So this will give me 1. Fine? Now 1 minus 0 will again give me what? 1. Right? And 0 minus lambda will give me what? Now I will take its determinant because I have to take the determinant of the result of the matrix kind of thing that we have done inside. So this will be equal to what? This will be equal to 0. Right? Now solve it. So you will get lambda square minus 1 equals 0. So what you will get? You will get lambda square minus 1 is equal to 0. This implies lambda is plus minus 1. Now see, I'm coming to that plus 1 and minus 1, indicating the problem that we are looking for. Now these are our energy eigenvalues. Now corresponding to each energy eigenvalue, what you have? You have energy eigenvectors. Do you have? How we calculate energy eigenvectors now? Okay, you have the case 1 now. Case 1. Yes? How will I calculate the energy eigenvector? Come on. So, for the case lambda is plus 1. Go back to the equation. What's my equation? That is sigma x. Then zeta is zeta simply. Because lambda I have taken plus 1. Are you getting it? Okay. Now what is this sigma x? And what is this zeta? It's a column vector. So sigma x is how much? Sigma x is 0, 0, 1, 1. And this I will call as zeta 1 and zeta 2. Any problem? This is equal to zeta 1 and zeta 2. I have two spin states, zeta 1 and zeta 2. Okay? Come on. Can you solve this now? Yeah? So this is 0 and zeta 2. For this is zeta 1 and 0. So in the top I'll get zeta 2, in the bottom I'll get zeta 1. So I'll have zeta 2, here I'll have zeta 1 is equal to what? Zeta 1 and zeta 2. Clear? Clear? So zeta 1 is equal to zeta 2. Zeta 1 is equal to what? Zeta 1 and zeta 2, they correspond to zeta, right? And zeta, I chose the solution. Zeta 1 plus zeta 2 is also the solution, right? Getting the point? So zeta 1 is equal to zeta 2. Then what is my zeta that I started with? What is that? That is superposition of zeta 1 and zeta 2. So can I write this zeta is alpha zeta 1 plus beta zeta 2. Are you getting this? It is the superposition of, and why I introduced alpha and beta? Because I have to normalize my wave function. I have to normalize it, right? So, provided this alpha square plus beta square is equal to 1.
सर एक सवाल है,
Yes.
जो zeta 1 था equal to है ना zeta 2 के बराबर, तो अगर आप उसको नॉर्मलाइज करना था तो हम उसको कांस्टेंट एक ही रखते अल्फा, हमें 2 क्यों रखे?
Keep it. I want that. I want that. Okay. So I will write down alpha square plus alpha square is equal to 1. So twice alpha square is equal to 1. So alpha square is equal to 1 by 2. So alpha is equal to 1 by root 2. This is what I wanted. You remember what I did yesterday? I started with spin up and I wrote it down by a matrix. A column matrix. What was that? 1 by root 2 and 1 by root 2. Are you getting my point? I'm trying to come back to that lecture that I gave yesterday. So what was that? So for having given zeta 1 and zeta 2 means 1 by root 2 times 1 and 1. So this will give you 1 by root 2 and 1 by root 2. Now this is my zeta. I represented it by what? Zeta. But you should represent it by zeta plus. Okay? Because then you have to do the same calculations for zeta minus. Are you getting my point? So here what I have is I have this zeta plus, and this zeta plus is 1 by root 2 and 1 by root 2. And this zeta plus is my get of spin up along x, which I wrote yesterday. I started from this yesterday. Right? Clear? I think it's enough. Any questions?
Yes, sir. Sir, अभी पीछे लीजिए.
Yes.
अभी हमने अब ये अल्फा बीटा के बराबर हमने रखा है. अभी तो हमने रखे थे ये अलग अलग, ये आप हमने क्यों रखा है फिर से?
Like you said, you were sure about it, right? You were sure about it, and that's the reality because zeta 1 is equal to zeta 2. Okay, what we obtained is zeta 1 is equal to zeta 2. So you can simply add up their normalization constants, and you will calculate their normalization constant from this. Okay.
हमें डिफरेंट नहीं रख सकते, सेम ही रखना है.